Hello everyone and welcome to Control Engineering and Control Theory tutorials. In this tutorial we explain how to derive the final value theorem. Or in other words, we explain how to mathematically prove the final value theorem. For those of you who are not familiar with the final value theorem, this is one of the fundamental and practical theorems in the linear control systems theory. Namely, this theorem is used to compute the steady-state errors, then it's used in control system design, then it's used in control system analysis, and it has a number of other applications that are fundamental for proper design and analysis of control algorithms. Consequently, it is of paramount importance to properly understand and know how to apply the final value theorem. And the best strategy to learn the final value theorem is to learn how to derive the final value theorem. Okay, so let's start. We consider lowercase y of t, and this is a time domain signal. Here, t is time. Then, if we apply the Laplace transform to this time domain signal, we will obtain uppercase or capital Y of s, and this is the Laplace transform of the time domain signal. Here, s is the complex Laplace variable. So here's the problem. Given the Laplace transformed signal, capital Y of s, without computing the inverse Laplace transform, that is, without going back to y of t, calculate the steady state value of y of t. That is, calculate y at infinity in the time domain. Again, someone gives you only the Laplace transform and asks you the following question. What is the steady state value in the time domain? And you should do that. That is, you should compute the steady state value without computing the inverse Laplace transform. Let's explain how to derive the final value theorem. But before we actually derive the final value theorem, it's very important to clearly and accurately state the final value theorem. The final value theorem has at least two equivalent statements, and here's the first statement. Let lowercase y of t be a time domain signal, and let uppercase or capital Y of s be its Laplace transform. Then assume that Laplace transform, capital Y of s, has all the poles in the open left half of the complex S-plane and at most one pole at the origin. Then the limit value when t goes to infinity, time domain signal y of t, is the limit value when s goes to 0, s multiplying Laplace transform y of s. Again, over here, capital Y of s is the Laplace transform of y of t. And this is the first statement. Here's the second statement of the final value theorem that's equivalent to the first one. Let y of t be a time domain signal and let capital Y of s be its Laplace transform. Then assume that the poles of s multiplying the Laplace transform y of s are in the open left half of the complex plane. Then we have limit value when t goes to infinity of the time domain signal y of t is actually limit value when s goes to 0 in the complex domain s multiplying y of s. And that's it. So what's the difference between the first and second statement? Well, these are equivalent statements. The only difference is in the assumption. Here it's assumed that the poles of s multiplying y of s are in the open left half of the complex S plane. Namely, if we multiply y of s by s, then any pole that is of multiplicity 1, that is any single pole at 0, will be cancelled, and then this assumption is actually equivalent to the main assumption of the first statement. That's it. The second statement is more elegant, however you should know both statements. Okay, let's learn how to derive the final value theorem. First of all, we introduce this assumption. All the poles of s multiplying Laplace transform y of s are in the open left half of the complex plane. And let's start from this assumption. To derive the final value theorem, we will use the very well-known rule for evaluating the Laplace transform, denoted like this, of the first derivative function. That is, we want to evaluate dy over dt. And in our previous lectures, we explained this formula. This formula is a pretty much standard formula that you can find in any textbook. The Laplace transform of the first derivative of y with respect to time is actually s multiplying the Laplace transform of y minus the initial condition, y of 0 minus. Okay, so this is a standard formula and we start from this formula. Next, we are going to apply the definition of the Laplace transform to the left-hand side over here. So we will write integral from 0 minus to infinity e to the minus st multiplying dy over dt. And integration is performed with respect to time. Again, this is just an application of the basic definition of the Laplace transform to this function. If this is any other function, for example, z, over here you will also see z. Good. Now, what's the next step? The next step is to apply the limit to left-hand side and to the right-hand side. Okay, so what we are going to do? We are going to take the limit when s goes to 0 of the left-hand side. And we have s multiplying capital Y of s minus y of 0 minus. And this is equal to the limit of the right-hand side. Limit of this integral 0 minus to infinity e to the minus st dy dt multiplying dt. Over here, this limit can go inside of the integral, and this limit only acts on this function since this function depends on s. All other terms are actually seen as a constant with respect from the perspective of taking limits. So over here, we have that the limit value of, let's put it like this, limit value when s goes to 0, e to the minus st is actually equal to 1. And let's use this fact over here. So by evaluating this limit, on the right-hand side, we will have an integral from 0 minus to infinity. E to the minus st becomes simply 1. And over here, let's see what do we have. We have dy over dt multiplying dt. So this is simply dy. Okay, our next task is to compute this integral. And here comes the assumption. Since we assume that all the poles of s multiplying y of s are in the open left half of the complex plane, this integral and the corresponding limit that you will see later on will actually exist. This assumption ensures that at infinity, y function in the time domain will be finite. It's not going to oscillate and it's not going to diverge to infinity. This is very important assumption. Okay, so let's continue. So what is an integral of 1 multiplying dy from 0 minus to infinity? This is actually a limit value when t goes to infinity of what? Of, let's put it like this, since I already evaluated this integral, it's going to be y of t minus y of 0 minus. That is y of the initial condition. Now, the main question is, how did I go from here to here? That is, how did I transform this integral into a limit value? Let me explain you this very important step. We want to evaluate this integral from 0 minus to infinity, 1 times dy. This integral belongs to a class of integrals involving infinite values. Consequently, we need to use limits to evaluate this integral. So we write this integral like this. Limit value when time goes to infinity, integral of dy, actually 1 multiplying dy, and the limits are from 0 minus, and look what happens here. The upper limit is not infinity anymore, the upper limit is t. Now, if we ignore this limit over here, we know how to compute this integral. This integral simply becomes, let's first write the limit value. It simply becomes y, right, since we have dy, and we have bounds. The bounds are from 0 minus to t. And finally, we obtain the limit value when t goes to infinity of y of t minus y of initial value, initial time. And here it is. Here it is. And that's precisely what's written over here. I raised this small derivation not to blur the main ideas of the main derivation. So let's start again where we stopped. We stopped over here, and we know how to derive every step. Now, let's now simplify this left-hand side. This limit value acts only on the first term. This is mainly because the second term is a constant. So we write limit value when s goes to 0, s multiplying y of s, and over here we have the initial condition. And similarly, we can transform the right-hand side. This limit value only acts on this function, so we have limit value when times goes to infinity, y of t, and over here we have minus y of 0 minus. Now, we can cancel this term and this term, so we obtain limit value when s goes to 0, s multiplying y of s is actually equal to limit value when time goes to infinity, y of t, and this is exactly y at infinity. And here it is. Here's our final value theorem. That's it. Simple as that. So limit value when s goes to 0, s multiplying capital Y of s is actually y at infinity. And that's it. Not too complex derivation, right? Okay, that would be all for today.